Okay, so next up is Mr. Schultz, Jack Schultz. He received his Bachelor's of Science degree in Chemical Engineering from the University of Texas at Austin in 1985. He worked 1 year as a field investigator for a drinking water program in the Tyler Regional Office before transferring to Austin. After arriving at the central office, he performed a variety of duties, including plan review, technical support, and enforcement for almost 30 years. Although he retired from TCEQ in 2013, he continues to work in the Texas Optimization Program as a contractor with the University of Texas at Arlington. He continues to develop various technical assistance and training materials for surface water treatment plant operators and TCEQ staff. He also provides training during top activities and works on a variety of special projects. Please welcome Jack Schultz.
Oh, they edited that. They left out the part where I ultimately rose to the rank of powerless mid-level manager. Okay, I'm going to talk about process control monitoring. It's the concepts and how they've kind of impacted you guys' day-to-day operations and the TCEQ rules as well. We're going to talk about the principles and concepts involved, and we're going to talk about how some of these things have impacted TCEQ rules. And as we go along, I want to talk a little bit about a few strategies you can use to implement the concepts. Basic process control loop. A guy a long time ago named Chuck Schwartz showed me this, and I thought it was so impressive. Process control loop involves monitoring the process, analyzing the data you create, making whatever adjustments that you need to make, but it doesn't end there. It goes back into the loop again, so you just go round and round and round and round. There's just really more than 3 steps. It's an infinite loop. Process control is a 3-stage process. You got to plan your process control strategy, incorporate whatever devices you need to collect the data that you need to collect, and then got to just, implement the program. Effective planning requires you to analyze the process, identifying the critical control points, and I want to talk about critical control points. Any time that you collect a piece of data that you use to control a critical process is a critical control point. Determine the monitoring results at each CCP and develop performance targets for each of those things you're monitoring, and identify potential corrective actions if you have something outside the range that's acceptable. Don talked about establishing record-keeping practices, so you've got to keep records of what's going on. And then to go back around the loop again, verify that the program is effective. Make whatever adjustments you need to make to it. Okay, process planning. What are my major treatment processes and my minor treatment processes? At surface water treatment plants, anything that results in pathogen removal or pathogen activation is a major treatment process. For groundwater systems, it's pretty much disinfection is a major unit process, okay? And while those things are major processes, there may be other processes that become major units, even major processes, even though they are not resulting in any public health, impact. For example, there are some groundwater systems that have iron and manganese in the source water. If you don't control the iron and manganese, you're going to be dealing with a huge customer water quality complaint problem, persistent and ongoing. So even though manganese itself or elevated iron doesn't pose an imminent public health threat down at lower levels, even higher levels produce a kind of a long-term threat, not a short-term threat. It may become a major treatment process for you. What you can analyze and what you can and can't analyze or control is a factor in what you have to monitor, and what are the variables at each monitoring point. What could impact the results? Chemical treatment, what chemicals am I applying, as Don was talking about? Why am I using them in the first place? And where are they injected and what monitoring is going on? The other thing that affects your planning is what the regulatory requirements are. There are certain things a lot of the process control monitoring we do is for us to adjust the treatment process, right? Make higher quality water. But some of the things that you guys have to do, it's because the regulations require you to do them. Okay? Where do I collect data at critical control points? Whenever I need to make a treatment decision, I need to collect data. I want to try to limit the number of variables. Let me give you an example. I'm putting chlorine in at 3 different application points in my treatment plant, and I'm monitoring the chlorine residual at the entry point to the distribution system because the regulations require you to. While that's an important monitoring point for water quality and for regulatory compliance, you need to be monitoring each one of those application points, because what happens at the end of the plant is affected by each one of those things individually. So you need to monitor each application point so that you can figure out what's going on at everywhere you're putting the chemical in. The other thing about that is you need to have a monitoring point that will allow you to quickly determine the impact of the change that you've made. At surface water treatment plants, there's the rapid mix Don was talking about. Then there's like a 15 to 20, 30-minute flocculation time. And then there's somewhere between 2 to 4 hour settling time, sometimes long as 6 hours. It's great to monitor the quality of the settled water coming off that sed basin, but that's not the only thing you should look at when you're monitoring whether I'm putting the right amount of coagulant in, because you make a coagulant change and you have to wait 6 or 8 hours to see the impact of that change. Find a monitoring parameter that you can use to monitor the effectiveness of the coagulation process before you have to wait for the whole treatment plant to finish filtering the water, okay? And then figure out which of the process control points are really important. There are some that are really important for process control, like chlorine immediately after you put the chlorine in. And there are some that are important for regulatory requirements, like I've got to monitor the performance of each individual filter, or I've got to monitor the performance of the combined filter effluent that Don was talking about. What data should I collect at each critical control point? And do I use the data to make a decision of some sort, or is it just regulatory requirements? If I'm not using the data to make a decision, or if I'm not using the data to comply with some TCQ requirement, what's the point of me spending my operator's resources monitoring that parameter? I mean, if there's some reason to run a test, run the test, and analyze the results, make whatever changes you need to make. But if you're not using the data for anything, call TCQ and say, are you making me do this for some reason? And they'll explain it to you if it's a regulatory requirement. If it's not a regulatory requirement, talk to management and see whether I really need to do this or not. I mean, don't do things you don't need to do. It's time consuming. It's resource intensive. How often do I need to collect the data? Basically, that's a question of how quickly did things change. If I'm a groundwater system and my pH of the water stays really constant, do I need to monitor every day? Do I need to monitor twice a day? Probably not. If I'm a surface water treatment plant where I put more coagulant in and my pH of the water can change, I may have to monitor more frequently, okay? And what are the regulatory requirements? If you're a surface water treatment plant, you are required to monitor the performance of each individual filter every 15 minutes. So you must monitor the filter every 15 minutes. If you're a membrane plant, you've got to collect data every 5 minutes. That's what it is. Membranes are 5-minute data. The reason membranes are 5-minute data is membranes typically go into backflush a lot more frequently than once every 3 days. And so you've got to get a 2 consecutive reading in order to know whether you've hit a tripwire that TCQ has set. If you backflush your filters every 45 minutes, you can do 15-minute monitoring, but you need to get TCQ's permission to reduce the monitoring so you have a piece of paper from TCQ to say, the rules say 5 minutes unless TCQ gives you permission to do something else. You got to get that written permission to do something else. Otherwise, it's 5 minutes. And what are the ranges I expect to see or what am I required to see? And that leads me to this next slide. What results do I expect to see? What ranges are acceptable? What are the critical levels that I'm going to take action if they exceed? Okay. So in this example, what I've got is a treatment plant that's using chloramines, and they want to leave the treatment plant at 2.5. Anything below 3 and anything above 1.5 is kind of acceptable to them. As long as the operator keeps that chlorine residual within that range, you wouldn't expect him to go make a change. But if it drops below 1 or 1.5, or it gets above 3, you may want to have him do some follow-up. So that initiates this slide. So what's the target? Typically the goal is set based on maximum level of public health protection. I want my turbidity to be 0 coming out of my filters, or 0.01. That's an economically difficult thing to do. So, man, I got to admit, when you talk about what my goals are, I want to maximize public health protection within at a reasonable cost. But you need to understand that getting the turbidity down below 0.14, 13 in that range, you're actually providing about 99% additional pathogen removal than if you operate at the 0.3 NTU level. So I can provide a 99.999% reduction in pathogens just by lowering my turbidity level from 0.3 to 0.15. If I can achieve that economically, I'm going to take advantage of that so that I don't have to build more stuff in order to protect the public health. I can optimize my treatment process so I don't have to build a more sophisticated treatment plant. So there are some economic reasons to do this, but it's just try to maximize public health protection is what our goal is. Maximize water quality. Acceptable range. Acceptable range, and in that previous slide I had 2. Here's critical control level 1. Here's critical control level 2. It's based on the minimum quality that I'm willing to accept before I have my operators do something different, to make a change. Whether that change may be, I want you to watch it more closely, move your monitoring from once every 4 hours to once every 2 hours or once every hour until we get back within the acceptable range. But once I hit critical level 2, when water quality becomes absolutely unacceptable to me, I want you to actually make a change in the treatment process. I want the water quality to improve to an acceptable level, which is that critical control level 1 point. Corrective action 1 is at critical control level 0.1. Corrective action 2 is at critical level 0.2. If I get down below 0.5, I'm going to have a regulatory violation if I don't fix it within 4 hours. When it hits 0.5, I want the operator on duty to call me and let me know that I've hit this critical trigger and what action he's taking so that I'll know, can be confident that we're going to be back into compliance before I have to go tell the public that we fell below acceptable levels for more than 4 hours. One's I'm exposing you to higher risk, and one is I've exposed you to such a high risk for such a prolonged period that I've got to tell you about it. Okay, I mean, I don't want them to ever get to 0.5, but I certainly want to be involved if they get there so that I know they're not there in 4 hours. Does that make sense? All right. Okay. Planning also has to include the record keeping that Don was talking about. I need enough data so that I can investigate what happened during an event, what might have caused the event, and what did I do to respond to the event, and was that response acceptable? What went wrong and what went right? There are some normal performance records you've got to keep because the regulations require them. For example, you've got to keep your SWMRs for 10 years. The data that goes into building your SWMRs, you got to keep for 3 years, that kind of stuff, okay? Document each critical level event occurrence. What were the operating conditions? What happened? The date and time and duration, how long did it take us to address it? The apparent cause of the event and what we took, and was it effective? And it's really important to keep these records. For me to keep these records, actually, I have transferred some of my particularly successful ahas to a little portable hard drive. And I've also transferred some of my, oh God, I don't want to do that again, to that portable hard drive. For example, one time I wanted to test to see what the alarm setting was on an online turbidimeter, and so I said, I want to take that turbidity up to 2.5. And so I sent the SCADA system a signal for 2.5 without me being aware that 2.5 tells the SCADA system, oh crap, and shut the plants down. So, I don't want to ever go into a plant again and run a test that's going to make the operators' lives a living hell for 15 minutes while I undo that damage from an artificial signal. So yeah, keep a record of what went really well and keep a record of what went really bad. Okay. Program review. Is my process management program working? Have the number of unacceptable conditions gone down? Was a response that I had particularly successful, or in my case, particularly catastrophic? And am I utilizing my data? If I'm not utilizing my data, I'm not sure that I want to expend the resources that are involved in collecting it and analyzing it. Okay? And basically, what should I change? Okay. So we're back to the process control loop once again, because the slide's really important. I was attending Clayton Nicolardi's, and he repeated a slide and got all worried that he'd repeated a slide. This is a really important slide to repeat. Collect data, analyze data, make whatever changes you need, collect more data. Okay? Even if you don't make a change, your decision is make no adjustment, re-monitor. Okay? Just go through that loop internally. For eternity. Effective monitoring requires properly located and installed monitoring taps. Don talked about some of the anomalies that he's seen. One of them that I've seen that seems to be fairly common is you have an IFE, you got a bank of eight filters, and you decide to put all your turbidimeters in a little cluster in the middle, and you run this 1-inch line 50 feet to the turbidimeter, and that sample line is running 200 mils a minute. It may take, through that 1-inch line, it may take you 45 minutes to get the sample from the furthest filter to the actual turbidimeter. That data point doesn't tell you much because there's all this stuff going on during that 45-minute period, and you're not seeing the immediate response. So have your sample lines be properly sized, have the proper length, have them, I've seen sample taps installed on top of the turbidimeter effluent. Man, air gets in there. And so you sample, your turbidity sample has got a bunch of air in it, and it gives you high turbidity readings. So, I've seen them on the bottom of the filtrate line where sediment occurs. And so you get spikes from sediment that really aren't reflective of what the water is going into the clear well. It's not a pathogen risk. So anyway, make sure your sampling taps are okay and properly installed. Have an appropriate monitoring frequency. Like I said, if things change rapidly, have a more rapid monitoring frequency. If things change slowly, do I really need all that data? I mean, is all that data really going to be useful for me? And then triggered monitoring. Critical level control, like I hit critical level 1, I want to increase my monitoring frequency. So don't feel uncomfortable about jumping up your monitoring frequency so you have a more precise data set to evaluate what's really going on. Appropriate instrumentation. There's online turbidimeters or online sensors, and then there's manual, which are lab or field tests, and then there are data loggers that you have to have, okay? And there needs to be a monitoring SOP. In fact, we'll get to this. In fact, there's a TCQ rule requiring you to have a monitoring SOP. So, monitoring sample taps. This is an example of what I use, and it's, even though the picture says 2 to 3 feet upstream and 2 to 3 feet downstream, remember Don was talking about mixing and how long it takes if you don't have good mixing to actually get a stable result? That's really important. I've seen plants where that distance needs to be 15 to 30 pipe diameters of length in order to get a result. The other thing I want to point out is I've got two chemicals going in here, within 4-6 feet of one another, okay? I've got a sample point between the two. My first sample point is upstream of the first chemical to know how much of a change I need, what do I need to do? I do something, and then I've got a sampling point downstream. Did I do the right thing? Then I'm going to put it in chemical 2. Sampling point 2 is what's going on at that point that I need to change with chemical 2. And then downstream, does this combination of chemicals achieve what I want to achieve? In this case, I've drawn this for systems using chloramines, where the first sample tap is the chlorine, or the first injection is chlorine, and the next injection is ammonia, LAS. One of the things that I need to point out to the operators is this is what's required by TCEQ rules, okay? Sample upstream of chlorine, downstream of chlorine, upstream of LAS, downstream of LAS, okay? The reality is that I need to be cognizant of the fact that if it only takes 15 seconds for the water to get from injection point 1 to injection point 2, is there any test that I can run that will pull the sample, analyze the result within 15 seconds? If there's not, competing reactions are going to occur. So the sample result that you get from tap 2 isn't really what's happening at the chemical injection point 2. The chlorine residual is going to be, for example, the chlorine residual is going to be higher than you get with the test method, because when you run your manual free chlorine test, there's all kinds of competing reactions that occur in the 30 seconds between the time you pull the sample, the time you add the reagent, the time you shake it up, the time you put it in the test kit and run the test. That water has already had ammonia added to it. So the number you get from that free chlorine test may not be the free chlorine number that actually exists at that water sample. The other thing you've got to make sure that you do is you get complete dispersion of chemical 1 before you have the tap for chemical 2. So if you can't get that complete dispersion, if there's no inline mixer to completely disperse that chemical, that 2 to 3 feet thing, that's kind of out the door. You need to understand what's going on. Okay. Monitoring frequency. Why am I collecting the data? Is it routine, or is it am I assessing the impact of a change? I'm going to monitor the pH of my coagulated water once every 4 hours or once every shift, just to see what my coagulation is doing to the pH of the water. Okay. If I change my coagulant dose by 15 or 20%, I may need to go out a few minutes later and pull that pH and make sure that I haven't overfed or underfed the alum, okay? So that my pH results stay within the line that I want it to be, my acceptable range for pH on my coagulated water, okay? Then there's always the regulatory requirement, okay? It's always going to hit you, okay? Frequent monitoring requires online instruments. Nobody's going to run down to the filter every 15 minutes and pull a sample off of each one of those 8 filters. You got to have online monitors to do that. Infrequently monitoring combined filter effluent. Large plants only have to do combined filter effluent once every 4 hours. Small plants even less than that. I can have an online CFE meter that's tied to my SCADA system, so my SCADA system knows when things are starting to go bad without my operator actually having to run out and run a test. I can use that online sample, but it's got to, what you report to TCEQ has to be at the designated 4-hour sample time. If the plant's not actually treating water at that 4-hour mark, you've got to go back to a period within that 4-hour window when it was actually treating water, so that result doesn't reflect a situation where the plant's been idle for the last 45 minutes, okay? That 4-hour mark is a 4-hour mark if the plant is in operation at that 4-hour window. If it's not, you got to go back and look. If it's been offline for that whole 4-hour period, there is no data point that you can collect in that 4-hour window that says, hey, my plant was operating and here's what the turbidity level was. on your monthly operating report, you'll put an X that says, I didn't make any water during this 4-hour window. Does that make sense? Okay. You need to distinguish between data that counts and data that doesn't count. That turbidimeter is going to keep reading the data whether the plant's running or not. So somewhere along the line, you have to have some way of saying the plant's making water or the plant's not making water. Some way to distinguish between data that counts from data that doesn't count. Okay. The accuracy, precision, and resolution of the instrument, both for online and grab samples. So let me talk a little bit about accuracy. Accuracy is the ability to get the right answer, okay? Precision is to get the same answer every darn time you run the test. Resolution is how close of a number can I get to what I'm looking for? And span is, can I sample the whole range? Okay, those are really important terms. So let me talk about visually precision and accuracy. Sample 1, I am precise because I get the same darn number every time, or really close to the same number, and I'm accurate. That number means something. The second sample is I've got real good precision, but the answer's wrong, okay? All right? The third number is if I run enough tests, I can get an answer that's right, but I have to average all my imprecise results to get it. And here's mathematically what we're looking at, okay? The average at 1 NT, I've got a 1 milligram per liter residual. In the first thing, I run all the tests and I get a 0.99 and my standard deviation is 0.1. I'm precise and accurate. The other test, I'm really accurate. My standard deviation is only 0.11, but my number's wrong. And then the last test, if I've run 7 samples, I'll get a number that's right, but any one value doesn't mean anything. You've got to run a whole bunch of tests to get the right number, and that's not a good method. Okay. Here's span and resolution. My operating range for my chlorine is 0.5 to 5.5 free chlorine. My minimum allowable residual is 0.2. These are samples where I get span only because I can't measure 0.2, or I get span only. I get resolution only because I can't go up above 5, and some of my numbers are, this doesn't have a pointer on it. Some of my numbers or my target residual, acceptable residual for me is 5.5, okay? And then method 4 gets me both. Okay, so what are the regulatory requirements? For individual filters, combined filters, and entry point residuals, there is a regulatory requirement that you have the ability to measure and record individual filter numbers from 0 to 2.2, because 2.0 is an action level, a critical action level that requires follow-up studies. Don talked about mandatory comprehensive performance evaluations. If your filters keep hitting 2.0, you're going to get a visit from TCEQ to help you figure out what's going on. You know, you can do it 1 month. If you can figure out what's going on and fix it, then we won't show up. But if you do it 2 months in a row, TCEQ is going to show up, and they're going to ask you administrative questions. They're going to ask you operational design, maintenance. They're going to ask you all kinds of questions. It's 4 or 5 people for 4 or 5 days. I mean, they spend a lot of time at the treatment plant trying to distinguish between a symptom and an underlying disease. What's the real problem? Okay? So they try to help you. But you'll notice that for span, for entry point disinfectant residual, it's 0 to, what's this number? The number is based on what you expect the maximum level is to reach the distribution system, because TCEQ or EPA, neither one of those agencies, have a maximum residual entering the distribution system. They have a running annual average for all of the samples collected throughout the distribution system averaged together, and they have a minimum entry point, but no maximum entry point. So as long as your average stays below the limit of 4, you can enter the system with 15, assuming you don't get customer complaints. Which, I have a war story, but I don't have time. Oh, darn. So anyway, Analysis. Data analysis requires you to present the data in a format that allows the operator to rapidly assess the results. Compare the results with the performance goals or acceptable range. And Don talked about SOPs. You need to have SOPs that tell the operators what these acceptable ranges are and what your expectations of him are. Okay? Real time, there's the HMI displays on the instruments. The SCADA system control room and the arm levels need to be tied to these whatever critical points that you want to set. The historical data needs to be accessible. We've visited plants where they've changed out the SCADA system, and the new SCADA system can't read the data file from the old SCADA system. So when the TCEQ investigator came out and asked for data that was 18 months old, the plant could not produce it, and they got cited for a violation. They still have it, but in order to do that, in order to access it, they have to take it out of they have to take their old SCADA, their new SCADA system offline, put their old SCADA system back in, and produce the report for TCEQ, and it's just not possible. So make sure that whatever format your data is stored in, the data that's 3 years old needs to be in some accessible file like XML or CSV, something that's readable by Excel or your new SCADA program, okay? And I tell operators the importance of, man, have management get your SCADA guy to produce reports for you so that you don't have to scroll down through 96 filter readings and turbidity readings off of each filter and figure out what the highest was, and then go over and look at the filter. Whether the filter was actually discharging into the clear well. No, it wasn't. Crap, that reading doesn't count. And they have to repeat that process. Having the SCADA system automate this with reports will save you somewhere between 2.5 to 5 hours a day of operator times at a large plant. At a small plant, it will be less than that because there's fewer filters they have to look at. You have 5-minute data for a membrane plant. It's going to take a lot longer if your SCADA system doesn't do these reports for you. Okay. SOP content, Don talked about it. SOPs need to have the title and version number. It needs to have the date that was originally adopted and the date of each revision. The objective, the equipment that you need to implement it, the step-by-step procedures. Now, step-by-step procedures, it can be refer to the Hawk manual for running free chlorine and follow those step-by-step procedures. And you don't have to repeat everything that's in an SOP somewhere else. Just reference that other SOP, okay? How to document and interpret the data, where you want the results recorded and what the action levels and responses are. And then the operators need to understand how to use the SOP, so be sure that you train them. And then periodically, I know TCEQ says every year, probably every couple of years you need to look at them. If the operators see that the SOP is not meeting their needs, accelerate that review process, bring it up to the top and review it. Okay. Adjustments. Making adjustments requires you have functional equipment. With most plants, that means automated SCADA equipment. But you also need to have the ability to manually adjust if you need to. Written SOP and instructions, it needs to include maintenance and calibration requirements. So all of these concepts of process control has had an impact on the TCEQ regulations. Facility design and PWS operations, okay? So let's take a look at groundwater design. The rules say you got to have meters for flow rate and production data. You got to have sample taps for all your treatment processes, and whatever your treatment processes are, you have to have the lab results. I mean, you have to have the laboratory capability. Now, TCEQ gets pretty flexible for groundwater systems where water quality is fairly constant. For example, if I've got manganese levels that are 0.24 or 0.024, and I want to treat it because I know that it accumulates in my distribution system and will ultimately cause me problems, I'm going to need to run a manganese test. But manganese levels really don't change that much. So maybe the TCEQ will not make you get a manganese test kit, Maybe they'll allow you to send it out to a laboratory because you may only need to check it once or twice a year. Make sure something hadn't changed. Okay? If I'm feeding orthophosphate to control my manganese, maybe TCEQ will say, hey, manganese levels are pretty constant. You're not fluctuating your orthophosphate every day. I'll let you send the orthophosphate sample out for phosphate testing. Okay? Special treatment processes like RO, and we'll talk about special treatment processes later. Okay? Surface water treatment plants, their water quality is a lot more variable. They've still got to have the meters and the sample taps, but now they got to have a lot more lab. You got to be able to run alkalinity, you got to be able to run pH, turbidity. If you've got a solids contact clarifier, you have to be able to measure the sludge depth or the solids concentration in your slurry, depending on whether you're running sludge blanket or slurry recirculation. Don talked a lot about the slurry recirculation clarifiers. For those clarifiers, it's not so much the importance of the sludge, depth of the sludge outside the skirt, it's the concentration of the solids in that slurry recirculation zone. If I don't build a high enough concentration of solids in that slurry recirculation zone, I'm never going to get a settleable flock that'll settle to the bottom of the basin. Okay? In a sludge blanket clarifier, that blanket of sludge around the center cone, that's the physical removal processes. So I need to be able to measure how deep that blanket is because that's really important. Not so much the solids concentration in the blanket, it's the depth of the blanket itself and what it looks like through the whole depth of the blanket. Okay? And Don talked about the plants we've seen where it's just this basin full of sludge with water zooming across the top of it. And the only reason it's not all full of sludge is that the velocity of the water coming across the top of scours the sludge and takes it over to the filters where it gets removed. Hopefully. At this plant, it wasn't. Anyway. So surface water treatment plants, you got to have IFE and CFE turbidimeters, loss of head gauges, but there are alternatives to loss of head gauges. Rate of flow controllers and limited slow opening valves. Don talked about you don't want to open that backwash valve right away and slap the crap out of it. You don't want hydraulic surges. You want when the filter comes online, you want to be able to ramp it up, ramp it down, do all that kind of stuff. Okay? Be able to drain the filter because you talked about doing the filter inspections. You got to be able to get the water out in order to go in the filter and inspect it. Recycling, if you provide it, must be done according to a plan that's been approved by the TCEQ. And whatever recycling approach you have, it needs to prevent hydraulic surges on the sedimentation process and the filtration process. So if I'm running a 1 million gallon a day plant with 1 million gallon a day raw water, I don't want to slap it with another 300,000 gallons of recycled water for 15 or 30 minutes. I want to bleed that recycle stream in at 100 gallons a minute over the course of 3 or 4 hours. Okay? Because that recycle stream is going to have an impact on the coagulation process and the disinfection process. Chemical feed systems, you got to be able to control the chemical feed, the disinfectant feed. Sampling taps before and after each chemical feed application point in the lab facilities to measure all the residual levels and disinfectant levels. Alternative processes, the regulations cover the monitoring requirements for conventional or the more common treatment processes. But man, we've got bags and cartridges, now we got membranes, now we got UV. When TCEQ writes permission to use alternative treatment technologies, they typically have an exception, and what that exception does is say, hey, I'm going to set site-specific monitoring requirements for this technology at this particular plant. Okay? Those practices, those requirements that are imposed by that exception become regulatory requirements. They become enforceable. So if you have an exception that says you're going to do X, Y, or Z, you must do X, Y, or Z at whatever frequency TCEQ told you to do them. If you don't, TCEQ will cite you for a violation of the rules and send you off to enforcement. So it's really important for you to understand what's in your exception. And if things are different and things have changed and that exception should be modified, talk to TCEQ and get that modification in writing. Okay? The field investigator can't do it, and I can't do it over the phone with you. It's got to be in writing. No print, no count. Okay? All right, storage tank. We've talked about treatment, but I want you to understand that this concept of process control affects just storage tanks and pressure tanks, and there are rules that say, hey, I have to be able to know what's going on in my storage tank. I've got to have a water level indicator, okay? I got to have a way of drain and clean the tank. I've got to have all this stuff so the operator can do what he needs to do to make safe drinking water, high quality drinking water. Same way with pressure tanks. It affects the distribution system. I don't know if you remember earlier in the day, if you went to the general session, Jason talked about capital improvement projects, and where he talked about you need to prioritize what you're going to do with your money. This is the same part of that. This whole process control thing extends beyond treatment or design. It affects everything. And then Russell talked about, he showed you the cutaway of that flush valve. I mean that control, that isolation valve, where it was all gummed up and wouldn't work. Man, if that valve is critical to your distribution system operation, you better make sure it works. We've been to plants where the folks went on a boil water notice because they drained their elevated storage tank because the flange on the elevated storage tank that allowed it to be drained, the vendor didn't put a valve on that. He just blind flanged it. So the only way to drain that tank so that they could do maintenance on it was to drain that water in the distribution system. They drew that water down and it peeled everything in that tank off the side of that tank, out of the bottom of the bowl of that tank, and sent it off to the customers. They had paved the roads and covered all their isolation valves. So they couldn't direct the water to a flush valve. The only way they could get it out was to send it to the customers. And they went on boil water notice. So anyway, I'm out of time. If there's it also could have process operation, PWS rules. If the questions and answers, okay. First person you ought to talk to, yeah, thanks, Don, pointing at his watch. First person you ought to talk to is your field investigator, or you can contact the Water Supply Division. This number, 239-4691, that's a really handy number. If you call that and tell the receptionist what you want, she will direct you to the staff member that can help you, okay? If all else fails, call me. But just bear in mind, I don't have any official answer. I can tell you what the rules intend, but I can't make an official determination. Be sure that if you've got a process control tap, you shouldn't be using that for compliance monitoring, because every sample that you take at that process control tap becomes a compliance determination. Okay? So have your compliance sample taps be distinct from your process monitoring sample taps. That was the point you were trying to make, right? Yes. That's a very good point. Man, it was hard not to curse during this.
Thank you, Jack.
Thank you very much for your attention.